So good morning, everyone. Welcome to the ECE Colloquium today. It is my great pleasure to introduce our three speakers today from IBM Research. Jim Cadden is a research staff member at IBM Research Cambridge, where he works on cloud security. He received his PhD in computer science from Boston University, and his current research is on advancing confidential computing in the public cloud through secure virtualization technologies. Tobin Feldman-Fistam is a software engineer at T.J. Watson IBM Research Center. He currently works on secure virtualization for hybrid cloud using various techniques in confidential computing, which includes support for encrypted disk images, fast live migration of confidential VMs, and extending confidential computing to containers. And Hubertus Frank is a distinguished research staff member at the T.J. Watson IBM Research Center, where he leads work over the last 30 years on HPC, Linux OS, computer architectures, and cloud security. He is an adjunct full professor at NYU and served for the last 8 years on the Rutgers ECE Industry Advisory Board. Before we start, one message to our audience is that you can ask questions at any time. You can either type in your question in the chat box on Zoom, or you can use the feature of raise hand on Zoom. So then our speakers will get to your questions as soon as they can. And if you choose to raise hand, you will have the opportunity to be unmuted and speak, and you can interact with our speakers. All right, so Jim, Tobin, and Hubertus, the stage is yours now. Please get started. Thank you.
Thanks, Sheng. So first of all, on behalf of the team, thank you very much for the invitation to present our work. You know, we have been affiliated with Rutgers for many years in various capacities, right? I've been on several of your programs, in projects, right, in meetings and so on. Okay, so let me go to the next page, Jim. So we're going to split this up a little bit between, I'm going to do a little setting of where we're coming from, why we're doing all of this stuff, and Jim and Tobin are going to dive into the technologies. Again, just talk into our presentations. I mean, we are pretty much used to it, right? So when we talk about confidential computing, the reality in our point is very scary, right? Who can you actually trust today, right? So I basically, in preparation, went to a web site and just basically looked at how many of intrusions and vulnerabilities have been discovered over the last 15 or so years, right? And if you just take the latest ones where you hope that actually things would become better, you can actually see it's actually getting worse, right? There is so much opportunity for somebody to break in systems in terms of getting access to private data, to confidential data, to financial data, that you know, at the end of the day, particularly when your personal data such as social security numbers or driver's license numbers are basically being exposed, you effectively are subject to, you know, identity loss and so on. I mean, I personally got hit by an identity loss when somebody tried to file an unemployment check for me, right? So if you look, for instance, even the big companies you would expect, they would tie down most of their data, like Facebook or banks, often are hit by cyber attacks, right? Now, on the right side, we have here an example when you talk to experts in this field. I like the term, what they're using. It used to be that cyber criminals went from the spray and pray effort, right? Now they're actually going very systematically in, they're planning their attack. Often it's a coordinated attack. And once they're getting access to your system, then the question is how strong or how big is the blast radius. Used to be that we only have databases, you know, hidden behind a particular server IP number and so on. So you could really put up a defense on that particular server. Okay. Nowadays, many of these things have been moving or are being moved to the cloud, and now the point is that once you basically start breaking into systems, the question is how fast is your blast radius? Because at least from our perspective, The environments on where systems are running are often shared, right? And as you're breaking in, you're not only breaking into the system itself, but you can also break into other people's systems as well, which are typically run as a virtual environment. Let me go to the next point and see where these bugs actually are, right? So if you really look at vulnerabilities and exposures that are often being posted in CVE databases, they're all over the place. That's my point here, right? So you can, for instance, go on the top left, we see that there are, for instance, Sql attacks, right? I mean, I've just cut a few out of here, and they often are ranked by severity. Once you break in, imagine somebody's breaking into the Social Security office and basically extracting Social Security number. It's basically instantaneous ID theft that you can do, okay? The attacks, if you go to the top middle, are often driven from either the network, so you're basically trying to do intrusions into the system, exploiting bugs that often exist in network and storage stacks, right? And therefore getting access to sensitive data. There are pretty much many of these attacks can be done through browsers, brute force, denial of service, right? Malwares, worms, right? And as intrusion and antivirus software is trying to basically fence against them, they're becoming significantly more sophisticated. When you effectively look at the bottom left, and I've been working in Linux for the better of 23 years now, right? You would hope that the system becomes more and more stable. The reality is that if you look over the last better of 10 years, actually the situation in a way has become worse, right? And that's typically due because we have more frequent updates, right? So like in 2017, there were major new features that were introduced in Linux. The code base is becoming significantly larger. And as a result, you see often these spikes of new vulnerabilities. And draw your attention to what is considered high vulnerability. If you go to the middle, bottom middle, this is not basically just limited to a single operating system. It's basically every operating system out there. And just here's another one that I dug out in terms of vulnerabilities that were reported in 2017. All major stacks are effectively contributing to these vulnerabilities. Then what you thought would be your last defense is the hardware. Actually, once we learned about Meltdown and Spectre virus, turned out that the hardware designers became overeager in optimizing just the last % of performance out of the chip and basically opening themselves up to side channel attacks, a whole new class that was discovered that way, which basically ran havoc through our system software. At the end, just to fix things up, many of the architectures that had exposures to this, as an example, in Linux needed to be fixed by software changes that often dragged performance down by 10–15%. So you see where sometimes overzealous optimization gets you. And another big contributor is a rogue operator, right? So imagine you're sitting in the cloud and you have an operator either intentionally or unintentionally misconfiguring your system, and all of a sudden you give access on your so-called private network to somebody else, since most of our networks are virtualized. So that shouldn't be discounted. Many corporations now even think that the insider attacks are more becoming a bigger threat than the outsider attacks as we start to learn how to defend our perimeter. Okay, going to the next slide, please. Right. So this has basically given the rise to a term what we call confidential computing, right? And for us in our department here, the idea is essentially how do we make, since we're cloud focused, how do we make this kind of confidential computing technology available, right? And the idea is essentially that we're using hardware and software technology to isolate customer data in protected enclaves while we're deploying them in the cloud. An enclave is essentially a piece of isolation, so to speak, right, that can be deployed, right? And the content in those enclaves is only accessible by the components that are authorized or that are trusted by the customer, and the customer can verify that, right? Most importantly, going back to the insider attacks, right, or through attacks that are done because of escapes from a particular customer environment, is that the cloud provider cannot get access to this enclave, That means he cannot peek and poke around into it, or if it's technically possible, he cannot make any sense out of the data that has been done. Okay, so in particular, the class of attacks that we are addressing here is the hypervisor breakout, right? Tobin or Jim will talk a little bit about more in a moment about it. An environment where the host is compromised, or when there is a physical attack. So as an example, somebody essentially shutting down the machine, taking it home and looking at the disk as an example, right? What we're not protecting against at this point is denial of service attack, okay? So you can actually learn significantly more about what our thinking in terms of confidential computing is when you go to the website that we have posted up here, right? We have various offerings in that environment. If you move to the next slide, what is actually the future of we call end-to-end confidentiality? So today, I would say we are looking at operational assurance, right? That essentially means the cloud provider will not access your data, right? So when we are deploying today, let's say virtual machine technology or container technology, we are basically stating the cloud provider will not access your data, right? What we really want to get to is what we call the technical assurance that the cloud provider cannot access your data, right? So this will guarantee, particularly when we're going into sensitive environments such as healthcare data, banking, which we often have very strong regulatory requirements that need to be met, right? So that we effectively can provide you this highest level of private assurance, right? That is, nobody can get your data. So overall, in our department, we're driving what we call towards a zero trust environment. And zero trust environment means you trust nothing, absolute nothing in your system, right? And I always equate this to my $20 bill. Hey, usually I use a $1 bill, but it's a $20 bill here, right? And it says, in God we trust and nobody else. And building a stack where you can literally assure your customer that there's zero trust that they have to put into our infrastructure is something where we would like to go to. Okay, and that's what we're gonna level out. Okay, next page. So there are basically three types of data protection that we're thinking about, right? If you want to limit what or actually completely prohibit what a cloud provider can use, right? They are typically protection for data at rest. That means in your file system, in your database, right? The other one is protection in transit. That's such as when you're communicating, right? And those two techniques are well understood, right? For instance, data at rest, we're using encrypted disks. For data in motion, we're using, let's say, TLS or secure communication. And the holy grail for a long time was how do we protect data in use? That basically means when we're computing on it, right? There are whole new classes of confidentiality that is basically done. But what we're seeing coming to the system right now is that hardware basically starts encrypting the memory of those enclaves, or hardware basically giving you physical isolation properties. So that means your cloud provider software, that means the whole software is completely separated from what is running in those enclaves. So there's no cross access from a hardware perspective. Next slide. So I think let me just high level provide you what, actually, no, this is a time when we're turning it over to Tobin, right?
I guess so.
Yeah, very good. Your turn.
Great. Thank you, Hubertus. So what are the tools that we have for confidential computing and for zero trust? As Hubertus has discussed, this is a pretty big challenge in how grave some of these attacks are and how many attack vectors there are, and trying to trust nobody while running, a modern application in the cloud. It's a pretty big challenge. So what are the tools? Well, they fall sort of into two categories, which are not really real categories so much as just a distinction that I made up. But there's sort of confidential computing and attestation, and they're linked. But when you look at confidential computing, generally what we're talking about is, as Hubertus said, protecting data that is in use, and isolating basically execution of operations on this data from execution of other operations and whatnot. So at the very basic level, when you have confidential computing, there's a bunch of different ways to do confidential computing, but they all have an enclave, right? They all have a protected area where you have your secret things, and they have, then there's everything else, and there are walls in between those two. So some ways that you can isolate those things, for instance, there's hardware memory encryption. So the memory that the enclave uses, where the confidential data will live when it's being operated on, is encrypted. There are other ways of protecting memory, of isolating memory that are not encryption, but hardware memory encryption is one of the more common ones. Some technologies also allow you to protect CPU state directly. So when execution switches from inside of the enclave to outside of the enclave, the CPU state is not left hanging around, but it's cleaned up and stored, usually in protected memory. There are also platforms that give you pretty strong guarantees about memory integrity, which means that when you're inside the enclave and you read memory, you can be sure that the value you read from memory will be the last value that you wrote to that memory and whatnot. So things outside of the enclave are not going to be able to do a replay attack or tamper with the memory in any way. But building walls is really only part of the question, right? You can have a very big castle, but if you don't know what's going on inside of it, that could be a problem. And so this is where attestation and measurement come in. And the idea here is that we want to measure, we want to be sure of what is actually going on and whatnot. So one way to do this, for instance, is to have boot time. So when you start up your enclave, you get a measurement of everything that happens in guest memory. Now, because you have strong walls around guest memory, you know that guest memory is only going to be modified from inside the enclave. If you verify it at boot time, you can be pretty sure that you're in control of it for the duration of the enclave. Now, like I said, there's a bunch of different approaches for confidential computing. The one that we're most focused on, and one that ticks all four of these things, is AMD SEV. One big thing about SEV is that it has the VM, well, the enclave for SEV is a virtual machine. There are other technologies like SGX, where that is not the case, where the enclave is drawn around different boundaries. But the ones we're mainly focused on are SEV and also TDX, where the enclave is a VM. So to zoom into the hardware memory encryption part of it, because this is one of the biggest pieces and the first piece that's being implemented by a lot of these tools. Like I said, the idea is that the memory inside of the enclave cannot be accessed by anything outside of the enclave. So in this case, right, enclave is a VM. So the memory inside of the guest can't be accessed by anything outside of the guest, including the hypervisor. And the way this is done is that there's a key for each enclave for the memory of it. The key is handled by something in hardware called the PSP, and that coordinates with the memory controller to make sure that the right key is being used at the right time when the enclave is executing versus when it is not. The host cannot do anything about that, can't tamper with it. We have, I think there's a picture on the next slide. Yeah, here we go. So, like I said, there's a piece of hardware. You can see it in green here. Maybe, Jim, you can cursor over the AMD secure processor. I'm not sure if it's green in real life, but the point is that there's a piece of hardware there that communicates with the memory controller and is going to make sure that the memory controller, which will do inline decryption and encryption that's fairly performant of memory, it's going to make sure that the right key is there at the right time. You can go to the next slide. So this is the walls part, right? This is the isolation part. The memory is encrypted. The key is only going to be accessed by the memory controller when the correct enclave is executing. But what about the making sure you know what's inside the castle part? Well, this is where measurement comes into play. So with SEV, as well as with TDX, but we'll think about SEV a little bit, you have processes for getting a measurement at boot. And the way this will work is that you can set up a secure channel between the guest owner, so not the host, but the actual person, your actual client, real person out there in the world who wants to start a VM with you for one reason or another. They can talk directly to the PSP, that's the AMD secure hardware, via a secure channel. The secure channel is set up via a key exchange. You know, the guest owner has a public key. The PSP also has a public key, and in fact has a chain of keys that will verify not just it will verify basically the trust of the PSP all the way down to making sure that, you know, it's actual AMD hardware run by the actual cloud provider and whatnot. Once you have that secure channel, you can get a measurement of the launch. Now, let's skip over the details here, but basically, you if you're doing memory protection only, which is the first generation of SEV, then the measurement will be all the memory that the guest starts with, which is the firmware. Basically, if you're also protecting CPU state, then you would get a measurement of the memory and the CPU state. There are also ways to extend this measurement to the init RD, the kernel command line, other aspects. There are ways to do encrypted boot so that you can be sure that the disk you're using is right too. But the point is that you verify it at boot, and that measurement is sent to the guest owner via secure channel. And the guest owner then has a chance to conditionally inject a secret, right? So if the measurement checks out, it can say, okay, well, here's this cryptographic information that my workload is going to need to maybe connect to some secure data service and pull down my secret data and whatnot, right? Basically, that's going to be the key that we're going to use to decrypt data that is encrypted while it's at rest and pull it into the enclave. This is a fairly high touch operation. So sometimes you might want some sort of proxy for the guest owner. You might want some other secure third-party automated thing in the cloud, could be another enclave, to carry out part of this handshake and part of the verification. So a guest owner proxy might figure in with that. You can go to the next slide. The trust model of all of this is really pretty interesting. We get really strong guarantees with confidential computing, right? When we don't trust the host, as Hubertus was saying, if someone breaks into the hypervisor, right? So very common attack vector on the cloud is that somebody figures out a way to use the interface between the hypervisor and the guest to actually influence control flow inside of the hypervisor. And that's pretty bad news because the hypervisor is controlling a bunch of different guests that might belong to different tenants. So gaining control of the hypervisor, if you're not the cloud service provider, is not ideal. But if all the other VMs are confidential and whatnot, if they're inside these enclaves that are inaccessible, doesn't really matter. Host compromise, more generally, if anything on the host is compromised, doesn't really matter. Even if the cloud service provider is not your friend, or if the FBI comes to them and says, hand over, this client's data and whatnot, well, it doesn't matter. They can't with confidential computing. And even if I were to go to the server itself and pull out the hard drive and take it home and plug it into my computer and get the drivers working and such, wouldn't matter because the memory is encrypted. That's pretty great. Not only do we have good walls, though, we also have proof of what's running. There are some complications, though, right? Not trusting the host, not trusting the hypervisor breaks a lot of things, and fundamentally means that we have to rethink the way that the host and the guest are going to collaborate at basically every level. So at the low level, this could mean things like I/O or encrypted disk or live migration, or more generally, para-virtualization, right? So anytime when the guest and the host are going to work together, for instance, if the hypervisor is connected to some sort of I/O device and is going to pass that I/O into the guest, well, we now have a situation where there is information is crossing the boundary, crossing the trust boundary from the untrusted host into the trusted enclave. And anytime that you cross the boundary, we need to be really careful and really think about what's happening there. Encrypted disk, traditionally, with encrypted disks and QEMU, for instance, the hypervisor is in charge of decrypting the disk and providing basically a normal looking disk to the guest, even though it's actually been encrypted on the outside. But of course, if we don't trust the hypervisor, we have to rethink how we do that. Live migration is a doozy of an example where live migration is a pretty complicated operation performed on a VM by the hypervisor, right? The hypervisor is in charge of handling the memory, handling the CPU state, moving it over to another node. And all of that goes out the window when you don't trust the hypervisor and whatnot. So you got to really rethink things. And like I said, in general, para-virtualization, bringing together the guest and the host, having the guest do some things to help out the host, you got to really think about how you do that. This continues at a higher level too. When you think about how the control plane is going to provision images for the guests and whatnot, well, if those are encrypted images, they have to be set up off-site in some trusted party. If you're not going to trust any of the cloud service provider, a lot really changes. Node selection, right? The cloud service provider is going to choose what node to put your VM on. Well, they got to choose a node that has the appropriate hardware and whatnot, or none of this is going to work. Key management, right? How are you actually going to get the keys inside? Maybe traditionally they would be stored in Kubernetes as secrets or something, but we don't trust the host. We don't trust the control panel. We don't trust Kubernetes, and Kubernetes secrets are no longer secret in this context. So the trust model is strong, but it really changes how we think about it at every level. And I think one of the things that's most exciting about this project, really, and about what we're doing, is that it's kind of fundamentally at odds with some of the ways that the traditional cloud is structured. And there's a lot of thinking and a lot of really interesting work to be done to understand how we can make this work and how we can get this great trust model and great guarantees and have that work all throughout the stack. And I think Jim will expand on this. I think that's it for me. We'll see what the next slide is.
Yes, thank you, Tobe. So continuing right along, the topic I'm going to be talking about to conclude our talk today will be how we're going to integrate all of this technology for confidential computing in the cloud. And Tobin framed it nicely that it's all about this guest-host relationship when we're talking about integration into a cloud service. And it's complicated by one of the fundamental characteristics of cloud computing is that the cloud provider is doing much of the work on behalf of the customers or on behalf of the clients. So in this metaphor of building a castle that's secure, you're building a castle that's secure that's in the cloud, and maybe you're asking the cloud provider to build the walls and furnish the throne room or something along those lines. It's now a very careful balance between getting the convenience of traditional cloud computing services, the ones that customers are expecting, the ones that customers have built their existing applications for, providing those traditional services, but doing it in a way that provides all of these advanced confidentiality features. So today, modern cloud providers are deploying these confidential computing hardware, namely the AMD SCV chips. They're available in IBM Cloud, in all the modern clouds, and they're beginning to offer these infrastructure as a service enhancements that are offering confidential enclaves through by the cloud provider. But the important shortcoming of all of the services available today that you with a credit card can go and provide is that you still have to trust the host and hypervisor to manage all the deployment and manage the guest encryption keys, which kind of at this point defeats the purpose. You're asking the cloud to create a protected enclave for you so that you don't have to trust the cloud, but then at the same time, in the same breath, you're trusting the cloud to set up and maintain and store all the meta information about that, including the encryption keys on behalf of the customer. So what we are looking to do is, or what we're building and what we're prototyping is this end-to-end complete confidential computing examples in cloud provider software. So what a cloud customer ideally wants that they cannot get today would be complete confidentiality, complete encryption and protection of their information from the time it leaves their data center or their on-prem to the moment it's deployed in the cloud, and done in an automatic way that maintains all the conveniences and the automation of cloud computing. So we are particularly looking at these our Red Hat hybrid container platforms, or hybrid cloud container orchestration platforms, which is Kubernetes and Red Hat OpenShift. We are looking at those as the platform that customer workloads or containers or pods are being deployed in the cloud. And how can we integrate that with with the confidential container virtual machines and all of the technology that Tobin just talked to? So a quick introduction of just the main difference here. So the virtual enclave provided by AMD SCV and provided by Intel TDX creates a virtual machine. So a full virtual machine that's running a guest operating system inside of it, all of the system libraries, and then the applications. And that's fine for a subset of cloud users. But the majority of new application models and new cloud services, such as platform as a service, software as a service, function as a service, uses a finer grain application model that is built around the functionality of containers. And in this sense, the operating system, the host operating system, is shared amongst multiple containers, and the applications, the customer applications, are bundled just with their immediate dependencies, such as their libraries and binaries, into a container image, which then can be easily migrated, deployed, replicated, scaled, etc. So this removes from the customer's responsibility the need to boot and manage an operating system, to apply security patches to a kernel, to do all of the things that are required for a virtual machine, or a full machine abstraction. So we have a bit of a mismatch in the models here. Customers want to deploy containers that just contain their application and their data sets, but they want to do it safely. They want to do it in a confidential manner. The confidential computing hardware requires you to boot a full virtual machine with a guest kernel, all of the software, and then of course on top of that you can boot the applications. So we have a what we call here is a building block for confidential computing. So this is what we are proposing as being the singleton piece that we can then work into existing systems. So this is what is given to us by the hardware and what we're trying to achieve. So we have a bare metal host with which is using KVM and QEMU to create a virtual enclave. And then inside that enclave, we're using encrypted memory with a guest operating system. And then inside it, we're running the customer's container or their pod. And in a pod is a Kubernetes terminology for a set of containers. And now you have a third item here, which is the cloud agent. And this is the piece of software that is run alongside one of these guest enclaves that is managing the larger cluster of deployment. So this is what's allowing a customer to say, just give a container image, and then that container image can be deployed across many machines simultaneously, or that container image can be brought up and brought down by the cloud provider as is required. So the question now is, where does this cloud agent live in regard to the guest VM enclave? So actually, let me skip to this one first. So there's two models that we are looking at in two existing pieces of software that exist in the open source that integrates or extends the Kubernetes and the OpenShift. So in Kubernetes and OpenShift, you get a cluster that deploys a number of containers across a number of machines. And traditionally, there are no virtual machines involved. In the KubeVirt extension, which is this is a Red Hat project, it allows you to take Kubernetes and deploy virtual machines with Kubernetes. So instead of giving a YAML, or instead of giving a spec for a container, you're giving a spec to define a virtual machine. So this is sort of a convenient way to give a customer a infrastructure as a service like platform where they can provide custom images and whatnot. The other one, and I'll get into a little more detail. The next one is the Kata container model, and this is what we're particularly focused on in this in our current project. This is deploying virtual machines, or I should say, this is deploying containers as virtual machines. So each container is deployed as normal. The virtual machine is created for the container to run inside, and it's a one-to-one relationship between a container pod and a virtual machine. So just clicking back here. So, and we also have two sort of ways that we're looking to do this. There's sort of two pathways. There is the fully encrypted one, which is the green, and the sort of partially encrypted one, which is in yellow. So in the yellow one, we can basically say, all right, I can give you a container image, or I can give you a virtual machine image. I can give it to the customer, or I can give it to the cloud provider, and the cloud provider can deploy it in an enclave. And that's good. But it doesn't provide that end-to-end security is what we're looking for. So in the green example, we have more components that have to come into play to provide the protection at rest and the protection in transit and at use And that's where we're looking into technologies like cloud HSMs, which provide secure key management on behalf of customers, and encrypted object stores where we are allowing the data to move from the customer's on-prem into the cloud in an encrypted way, and then deploy it inside one of these encrypted VMs, all without leaking the keys or the actual decryption mechanisms to the host or to the hypervisor. So this is where things get, we have some backup slides here if we want to dive into it, but this is where the sort of procedure graph gets complicated. So with KubeVirt, KubeVirt is a natural extension of the SEV, or a natural way to apply SEV, I should say. So KubeVirt extends the Kubernetes API to allow you to define virtual machine instances. So instead of specifying a container image, you're specifying a boot image for a virtual machine, and you're saying how much RAM and how many virtual CPUs that virtual machine should have. So we've built a customer VN object. Okay, so we've built a spec, or we built a set of patches for a prototype and take that existing API and add just a flag to enable the basic. This would be the yellow pathway. Just add a basic memory encryption ability onto KubeVirt. So now customers can, or clients who are running, who have access to a Kubernetes server, can specify, deploy this virtual machine image, but do it in an encrypted way, or create an encrypted enclave. So this is very convenient and fast, but it doesn't provide the end-to-end encryption that we're looking for. So what we would next do, or what we're looking into, is allowing encrypted images to deploy through this way. So the customer can give a encrypted file system image for a virtual machine that can then be stored safely in the cloud, and then a decryption key can be injected in as the secret into the virtual machine, at the time of the deployment. So that's one thing. It also it still kind of conforms more towards the older model of the cloud, where the customer is providing virtual machines, maintaining virtual machines. The next one that we're actively focused on is the Kata container model, which takes an existing OpenShift or Kubernetes cluster. This can actually run alongside KubeVirt or alongside normal containers. But in this case, customers are deploying regular unmodified container images through the standard Kubernetes API, and the virtual machine isolation is happening transparently. So instead of just a container on the local operating system being deployed, a virtual machine is being deployed, which contains just that container or just that pod. So we have been working with the open source Kata container community, with members of Red Hat and Intel, to provide this basic SEV memory encryption into the Kata containers that are being deployed. So this is currently a pull request that is under review in the open source, and there's a whole initiative that IBM is part of to create this notion of confidential containers. And especially with containers, more so than with virtual machines, this notion of the guest and the host relationship is complicated, because the agent, that teal colored circle that I pointed out earlier, the agent is actually running inside of the virtual machine instance. So here's a very high level of how Kata containers works. The Kubernetes kubelet talks to container D, which is the OCI container runtime. That, which would normally talk to the operating system to create a container, talks to a Kata runtime shim in the case of Kata containers, and that shim is talking inside to an agent that exists inside the virtual machine. So now this agent is running inside the encrypted domain, inside the trust domain of the customer. So this immediately, if you don't trust that agent, or if that agent is at all malicious, it breaks everything, because the customer is giving a pod. They don't know, they are not providing the agent. They are not providing, for that matter, the guest kernel or the initRD. The customer is only providing a pod or a container image. The rest is being provided by Kata containers, by the cloud platform, by the cloud service provider. So we need to find a way very quickly to trust that Kata agent, and both to trust it, but also to make sure that it can't do anything nefarious to the containers if someone on the outside is acting in as an attacker or in a malicious way. So by nature, or by the design of confidential computing, we don't trust entirely the kubelet or containerd or the Kata runtime shim. We trust them partially to not do denial of service attacks, but we don't trust them to maintain the privacy of what's running inside the pod. The Kata agent itself, we do have to trust, because if not, there is no hope. So some of the things that the Kata agent does by default that are causing immediate conflicts with this trust model is it's the Kata agent responsible for creating and destroying and restarting containers. It's responsible for traversing carrying the IO streams in and out of the virtual machine instance on behalf of the pods. It also does monitoring and tracing of the pods. So this is sort of the space where we're discussing amongst ourselves, discussing with potential customers, and also with the Kata community about what needs to change in this model to make it a truly confidential container. So we have a roadmap that is part of our current project, the roadmap towards confidential containers. So the first piece of that is the simple memory encryption, and this is something that has already been developed between our team and some engineers at AMD, and that is what's under review and very likely to be merged into the Kata community upstream sometime next month. Now, what Tobin and I are working on actively internal to IBM is a way to inject or a way to boot the agent, boot the virtual machine, and use attestation so that the the container owner can verify that the guest image, the initRD, and the Kata agent are the versions that they think it is. So if we can prove to them, one, that there's a safe version of the Kata agent, a safe version of the initRD, and a safe version of the guest kernel, one that cannot be manipulated, we're providing now the mechanism that once that container is deployed, that container can be assured that the safe versions of these pieces of provider software are actually what are deployed alongside them. The next piece to create this end-to-end confidentiality is to use an encrypted container image. So we have another researcher at IBM, Brandon Lum, who him and his team have worked on creating encryption layers built into container images. So you can have a generic image, but has the upper layers that contain customer data be encrypted. So the idea here is we can take that existing technology or that previous work and move it inside the enclave and do the encryption, do the decryption inside this SEV protected enclave. So now the customer can provide from their premises, they can provide an encrypted virtual machine, or an encrypted container image, and then know that encrypted container image can be uploaded to the public cloud without concern because it's encrypted, and it won't be decrypted until it's running safely inside one of these virtual enclaves. So we're working with or the existing SEV team and SEV technology to inject a key inside, basically pass a key to the Kata agent once after the agent has been attested and validated to decrypt that virtual machine. We're also collaborating with the Z technology team, which is a brand of IBM hardware that are doing something very similar in their IBM cloud services. And then the final phase, which we're going to get to likely this summer, is how to harden the guest host interface, the existing guest host interface between the Kata container and the shim, or the whole untrusted environment that runs outside there. So right now, for example, the agent that runs inside the container has the ability to get a command from the outside to run arbitrary execution. This is a common use for debugging and troubleshooting in Kata containers in Kubernetes in general. So obviously, if we're running in a trusted environment or a protected environment, we can't allow the cloud provider to run arbitrary commands inside our enclave. So this is going to be an interesting process, because we're going to be working with the community at large to say, how can we sort of selectively disable features without breaking Kata containers in general, or without breaking the interface across all other workloads. And part of the challenge here is that to get this feature eventually into IBM Cloud and into the Red Hat products, we need to get this functionality into the Kata container upstream. This is sort of one of the rules of the companies, is that these features cannot be just a research prototype. We need to get something that is accepted into the wider upstream community, so then it can be deployed into the actual productized version. So we have to come up with solutions that both provide the security guarantees that we want, but also aren't just quick hacks to get something that works. So it's going to involve some discussion and debate, and I'm looking forward to that. So that is both the what we're currently working on today, and also what we're looking forward to in the coming months. So at that point, I am reaching the end of the slides I have to cover, but we are.
I just want to mention that I think there was one slide in the presentation that said IBM Confidential at the bottom of it, but that did not contain confidential information. So we will not be having to wipe anyone's memory today, unless we screw up in the next 10 minutes. But have no fear. That was just generic information from another slideshow that may have had secrets in it, but that is not secret. You can know this.
That is not confidential. My mistake. Okay, well, thank you very much. That concludes our talk.
Okay, thank you, Jim, Tobin, and Hubertus for the great presentation. So we have plenty of time to ask questions. So please either type in your questions or please raise your hand so we can answer your questions. So any questions from the audience? So maybe I can start with one question, and then we can have some follow-up discussions with the audience. So my understanding of the confidential computing you talk about in the cloud is that, of course, it mostly focuses on the confidentiality of data. But I think I see, to some extent, it also could protect the integrity of data, meaning the data won't be maliciously modified, right, by, say, untrusted cloud providers or other adversaries. So can you comment on how the integrity is ensured, right, in this confidential computing environment? Because to me, the looks like only the encryption may not be enough, right, to ensure integrity.
Sure. Let me take this on, right? So when you're looking at integrity, ultimately, for those who are not familiar with many of these terms, it essentially means that nobody can modify your data unbeknownst to you, right? So when you're looking at hardware, the latest versions, for instance, of AMD SEV, which is our prime target at this point to work with because it's available, it's called the Milan system or S&P system that came out GA about 3 months ago, I believe, or 2 months ago. And that effectively provides you the integrity. So that essentially means that when, for instance, the cloud provider or any kind of software piece, most likely the hypervisor, host OS, or will touch your memory that has been designated to your VM, the VM will be notified, right? And so that's number one. Number two, when you're looking at other data, you basically do continuous attestation, right? As an example, when somebody modifies your boot disk or your data, you will get notification about it, right? Those kind of things that you have to level through your entire stack. But I fully agree. Confidentiality and integrity are the two pieces that absolutely need to be enforced, right? Some can be enforced by hardware, some cannot be enforced by hardware, and so you have to put software mechanisms in place. As I think James or Jim or Tom mentioned, is like at the end of the day, you're always in this predicament, right? To a degree, in order to manage something, you have to have a foot in it. And the Kata container was like the prime example, right? In order to squeeze yourself into a particular environment that was essentially provided, let's say, with Kubernetes, you have to have these agents sitting right next to your pod. At the same point, if you want to have insights, as an example, what we're doing in our cloud is we're continuously measuring and inspecting cloud images, right? Let's say you have a container image and you want to make sure that you have currently learned something, that there's a vulnerability has been detected in one layer of your container image, right? Let's say that was the base is like an Ubuntu image, right? That has identified a bug somewhere. They do an update, right? So we want to effectively see whether there is you're running software that is outdated, that has been modified as or has been identified as having a vulnerability, and essentially notifying the customer to it. That's number one. Number two, what you also will see in the industry here is that what we call a shift left, right? A shift left essentially means catch errors as early as possible. So an example that I just stated, where you're effectively using layers of images or container images, right, that don't vibe with each other, version conflicts, things like that, you want to catch before they're even deployed, right? And so what we have focused right now, and because we are an infrastructure team in a sense, we're working from the bottom up via architecture and operating systems, right? And basically penetrating into higher levels of the cloud management, so to speak, right? But the whole DevOps operations coming from the left-hand side, you know, is doing also their part, doing exactly what I just said, is shift left, early inspections, and having then policy in place, you know, where let's say it's not just the cloud provider and the end user or the end programmer, it's also the policies that, let's say, an organization puts in place that uses your cloud, right? So that if you want to deploy something, there might be a filter that says you can't do that, right? It's like, think about it, what happens if you don't change your password? At least in our corporation, if you don't change your password after the duty cycle of doing it, you get a notification. After a while, you get your manager gets a notification, right? So if you basically engage in practices that potentially sacrifice security, you know, there will be a notification process. But that's are things that companies who are using the cloud want to have tools to put in place, right? And that's ultimately what we're putting into our environments.
One thing that I would say about attestation is that traditionally, when you think about attestation sometimes, and you think about continuous attestation, there's this idea that you can sort of challenge a workload at any time, or maybe you're going to build some huge log and whatnot, and you're going to keep track of everything that's going to happen. You're going to have a boot log, and then you have a log of everything that runs on top of that. And it's something that you can maybe inspect after the fact to verify what's running. With confidential computing, things tend to be more focused on attesting something at the beginning And then in a lot of ways, the hardware technologies that you get kind of free you from having to do all this messing around later on and continuously and whatnot. Now, as you say, just doing memory encryption doesn't necessarily give you integrity of memory. So that does not give you integrity, although it should be noted that with SEV, for instance, you can't just put arbitrary memory into a VM because it won't decrypt, and you cannot move memory around in a VM because it won't decrypt, but you could do a replay attack where you put an older version of a page on top of a newer version of a page. But either way, with SEV SNP, as Hubert mentioned, you can't do that. So you get integrity protection of the memory. And then that basically, then you just need to attest what you start with, and you need to scrutinize every interface that crosses the boundary from the enclave. And then you should hypothetically be in control of what's running inside of the enclave.
All right. Yeah. Thank you so much for the very comprehensive answer. I really appreciate that. So are there any other questions from the audience?
We were trying to give people some time to think of things.
Yeah. Yeah, I think there's a lot of information for us to digest. I think maybe there's another question. So I think our students learn from some of their security courses about SGX because that is a pretty popular security mechanism here. Like there's a lot of work, a lot of papers on the topic of SGX. Maybe you can let us know about what is the major difference, right, between SGX and the SEV and the TDX that you are talking about. What is the relationship?
Okay, I'll take this one.
You want to do that, Jim?
Sure. So SGX has been around for a handful of years, maybe 5 or 6 years. And I view SGX as sort of the initial generation of the confidential computing hardware. And with SGX, you can encrypt regions of memory, and then an application such as a NoSQL database can store sensitive data inside that encrypted region of memory. And that in very similar way, it's the hardware, it's chips on the hardware that are doing the encryption and the decryption, and no one outside that application can read or get access to that memory. The key difference here, the key differential, is that it's just portions of an application's address space, not the entire address space of the application. So you need to write or modify your applications to start to take advantage of these special system calls that are basically allowing you to enter and exit the enclave memory of the application. So you're modifying your existing applications to be an SGX application. And I presume that one of the major pushbacks from this being widely adopted was people saying, well, what about all of my existing infrastructure software? What about all of the applications that already exist on GitHub or in Docker repos? I don't want to have to modify each one to make it an SGX application. So AMD, SEV, Intel, TDX, they're expanding the area that is encrypted, not just to be a portion of a single process's address space, but to be the entire memory footprint of a virtual machine. So you get the same encryption benefits, but you also get the convenience of just deploying your entire application, your entire file system, all of your data, both in use in the application also, or at rest in the files on your file system, deploying all of that inside an encrypted VM, and you don't have to worry about modifying individual applications to take advantage of this. So you can deploy all of your applications at once, and they're all sort of existing in the same encryption domain.
SGX does have some advantages, though, I would say. I mean, the mainly small TCP, right? So being able to be very surgical about what are the secure parts is nice. And being able to design an application where you say just this function is protected, that potentially gives you really good security guarantees. But as Jim was saying, there's a cost to doing that. And I know there has been work, I think maybe even at this institution, about automatically partitioning applications into secure and non-secure portions. I don't think that has quite hit the business world yet. And so the reality is it costs a lot. Now, I will say that there are also some platforms that try and support containers with SGX, like X containers and Scone and whatnot. And I think Scone is even used in production in some places. And here you start to hit capacity issues. So SGX has sort of low memory requirements, although I think that newer Intel machines have larger capacities for enclave memory. But when it started out, there was a pretty big stumbling block. There also are really interesting questions when you start to look at like putting containers inside of SGX about where you put the boundary. For instance, if you only put the container inside of the enclave, then the interface between the enclave and the host is the syscall interface, and that is potentially vulnerable to something, the so-called Iago attacks, where you can manipulate the syscalls to manipulate control flow or exfiltrate information inside of the enclave, which is not ideal. And then if you put more stuff inside of the guest, like maybe some sort of unikernel or libOS, to change the interface and make the interface less rich, well, then you have more stuff inside the enclave and you have size problems and there's more overhead and whatnot. So there have been attempts to make it more universal, but there are just problems with that. So if I were a betting man, there are some business reasons why, SGX is expensive, but it is an interesting technology. And I mean, we've thought a lot about the trade-offs, the TCB size, how this boundary should be, how you should measure the boundary, how you should understand the security properties of these systems. And SGX is interesting. Also, one final thing is that TDX is partly bootstrapped from SGX.
TDX is sort of the logical extension of SGX, and SGX, for that matter, is deployed in public clouds today. IBM Cloud has it. I know Microsoft Azure, and the way that they enable it with customers is to say that, hey, we have a SGX modified or an SGX enabled version of the Cassandra database or the MySQL database or MySQL. And if you use our packages, it has already been, extended to be able to use SGX enclaves. So if you're using data stores, then just use one of their flavored versions that have the ability to communicate with the SGX domain.
I see. Okay, thank you. Are there any other questions from the audience? I guess I have a lot of questions, actually. Maybe if time allows, I want to ask maybe another one.
Sure.
So, so we're talking about this end-to-end encryption, right? So I'm understanding that one end is from the user end, right? User probably encrypt their data before offloading it to the server, to the cloud. But the other end is a cloud provider, which the users may not trust. And so I think that's a point of confidential computing. But the other end, I think, is very challenging because eventually this cloud provider would eventually decrypt the data and to be able to do the computation, right? So there's probably a kind of a traceable moment where the data would stay in the clear. And
no, actually,
the cloud. Yeah.
It doesn't actually, right? So we had one slide, which that was the one that we have, the confidential slide, right? So the way this often operates is that customers can allocate themselves a slice of the, let's say, of a key management, right? So like an HSM, what we call them, right? And that's completely protected in hardware. So as an example, even as a cloud provider, you can't get access to the keys. You just can't. They're encrypted, right? And they're encrypted by hardware. If you actually go back and we had, like, maybe for the last 15, 20 years, we have a device that even if you look at it the wrong way, you put a screwdriver right next to it, it basically will shut down. And I'm not kidding, right? And it's really because it goes to the point where people literally take the chip, deep freeze it, right, in nitric glycogen and start skinning off the layers of the chip just to see what the current state of memory is, ultimately getting that. So that's truly a physical attack, right? But in general, in these key management systems, that's literally a slice of a hardware piece that you're being given to a customer, right? Just like you do a secure shell, you're literally shelling, or you're really connecting into that particular chip. The rest is just infrastructure group around that allows you to do that, right? And so what we're effectively doing is essentially taking many of these key managements that Tobin and Jim have talked about and connecting to that HSM, right? So from an end-to-end flow, the customer on his side will build his data. He's built his image. It's going to encrypt them and upload the key. right? That's one, right? So you bring your own key, you install that key in a secure fashion inside those hardware security devices, okay? And we always joke about the litmus test if the FBI walks up to the cloud provider and say, give me the keys, you can't do that. There's just no way to do it.
All right, yeah.
Right, so it doesn't matter whether you come with a warrant or with a gun, it doesn't matter, you can't do it, right? And so basically building this whole chain together where it essentially allows a customer to A, own one of those things, B, install the keys into it, right, as part of a bring your own key, and then ultimately tying the whole deployment of a virtual machine, what we call the building blocks under, for instance, AMD SEV or finally TDX, so that they can securely retrieve the key. That's just one of the infrastructure challenges we have, right? But at the end, it all boils down to establishing secure channels, which we know how to do. We do it every day, right, using our HTTPS browsers, right? And it's just basically putting all of these things together. Jim, Tobin, you want to add something?
Well, I mean, if we look just at just an SEV VM, right, the simplest possible thing. So we're going to boot the VM. We're going to get the measurement of the guest firmware and whatnot. We'll skip over how we measure everything, but let's assume that we know it's running. We're going to inject the secret via the secure channel, right? There's a secure channel between the guest owner and the PSP, the hardware. Now, fair enough, you might say, I don't actually trust the hardware. You got to trust the manufacturer, AMD's hardware in this case. That's where the root of trust is, though. There's hardware root of trust that will inject some secret material that's encrypted. The host has no way of reading that. Cloud service provider has no way of reading that. It will inject it to a guest physical address. So it injects it into guest memory. Now, guest memory is protected via memory encryption. The host has no way of reading that. Let's say that you perform some operation on the data that pulls it into a register. Well, with SEV ES, which is encrypted state, the CPU state is protected. Essentially, when there is some sort of switch, a world switch to outside of the enclave, all of the CPU state will be encrypted and put in encrypted memory. So if you examine the registers after this happened, doesn't matter, they're empty, and whatnot. I mean, I think that those are sort of the main channels. The place that you have to be somewhat worried about is the interface between the host and the guest, right? Okay, you're not going to be able to see the CPU state normally, but let's say you have some VM exit that you make some VM exit and there is some state that is provided to the hypervisor by the guest. That's part of the interface between the guest and the host. And that is a place where information could potentially leak out. But as long as you've secured that interface, as long as you've measured the things that are going into it, the host really should not be able to access the secret that you've injected. And that, we basically just bootstrap that hardware root of trust up into Kata, up into containers to do a bigger measurement so that we can have more stuff that's booted and also to have more stuff that we can pull in as a secret from that secure channel.
I see. Okay, thank you so much. I think we went over time, but I treat that as a kind of bonus time for having 3 excellent speakers for today's presentation. Thank you all for your time to give us this excellent talk and also taking the questions. Thank you everyone for attending today's colloquium. And we'll stop here. We'll hope we can keep in touch on the future research activities. Thank you.
Thank you.
Thank you, everyone.
Bye.
Bye.